Well, yeah, thanks so much for having me, Jonathan. I really appreciate it. Thanks for those of you guys who are here. So yeah, I'm Dan Chavas. I'm at Purdue. I'll be talking about tropical cyclones and Earth-like planets. Tropical cyclones is the main focus of my research through my career. And so this is just a nice movie that I'll come back to right now, looking at visible and infrared satellite imagery from GOES 16. This is from 2017, looking down at Earth, where you can see a couple of hurricanes, Irma and Jose. So I study Earth, and in particular hurricanes. So I'm highlighting them here and over the tropical Atlantic Ocean here back in 2017. And so one of the things that I did, which I'll be talking about, which was really fully, I was interested in understanding how hurricanes work on our real Earth. And to do so, I created some imaginary alternative Earths. And at the time, I had absolutely no thought to relevance to planetary science, but I realized over time that this may accidentally be relevant to other planets. So this is where I'm happy to share some of this work with you guys today. I wanted to note, my wife just told me this last night. So I have a 3-year-old daughter, and we have a solar system book. And at the end of the book, it says, the solar system is an exciting place. Where do you like to go first? And my daughter said, I want to go to Jupiter with Daddy because it's the one with the storms, which I thought was awesome. My daughter is awesome. So that was a nice lead in to being able to talk with you all here. So I'll give first just an introduction to a tropical cyclone. I'm actually hoping to convince you at the end of the day to think about, if you're interested in atmospheres of other planets, that tropical cyclones are a phenomenon that may very well be prevalent on other planets. And so what is a tropical cyclone? The similar words, hurricane, typhoon, they all mean the same thing. I'm actually going to kind of jump between tropical cyclone and hurricane. And just a note is that I'll give some intro here. I have a full hour grad level intro video on my YouTube channel if you want to learn more details, or you can just email me as well. So what is a hurricane? So this is a nice cartoon view of a 3-dimensional transect through a tropical cyclone. So the satellite view on the top. So there's an eye at the center. We have a kind of a circular shaped cloud shield at the top of the troposphere. And then the colors here are showing the rotating winds that get stronger as you move. So the strongest winds are found towards the center and near the surface. So, and then the winds decrease radially outwards from there. And so what's the flow doing here? So first of all, as we think about hurricanes, you often think about heavy rainfall and strong winds. So you can see the strong winds in the colors. This is just to give you a sense of the overturning circulation superimposed upon the rotating circulation. So there's a narrow inner convecting region where air rises quickly and you get heavy rainfall. And then you have an broader outer non-convecting region where air is subsiding slowly and there's generally no rain or little or no rain. So just to highlight the inflow and upflow branches of this. So you have air flowing inwards, and near where the winds are the strongest is where there's surface heat fluxes, principally evaporation on the present day Earth. That are quite strong, and surface heat fluxes depend on the wind speed. They increase with wind speed, which is really important for hurricanes. So there's significant heat input into the system where the winds are the strongest. And then in inputting heat, you're also rapidly saturating air, and then air then rises buoyantly in the ascending branch of the overturning circulation. And by having air rising inwards, you're drawing more air inward, or excuse me, as you have air rise upwards, you draw more air inwards, and with it more higher angular momentum air. And so this is kind of the crux of what's essentially a self-sustaining overturning circulation. So to put it in simple words, a tropical cyclone is a rapidly rotating convective vortex that's really driven by surface heat fluxes. Without getting too technical, so heat input from the surface is used to power the circulation against surface frictional dissipation, which is trying to slow the circulation down. And you can actually model this as a Carnot cycle. And what this does is gives you an upper bound on a thermodynamic upper bound on the maximum wind speed in a hurricane. So I'll actually come back to that in a second. So what's a really general point that I want to highlight is that these ingredients exist really in any atmosphere that's heated from below and cooled from above, which implies that you need to have a heat flux into the atmosphere from the surface. And in particular, I should actually say, and also that has background rotation. So on the F plane, actually in a homogeneous, otherwise horizontally homogeneous F-plane over an ocean surface, tropical cyclones will form spontaneously. And so that's what this movie is showing here from a recent paper of ours, and many other people have shown this. So these tend to form quite easily if given the right ingredients, and those ingredients are not that complicated. Just very briefly, what does the radial structure of the wind field in a hurricane look like? So this is an example from Hurricane Katrina of observational data of the rotating wind speed on the y-axis as a function of radius on the x-axis. And so you can see there's the maximum wind, the peak wind speed, and that's what corresponds to when you hear about category 1, 2, 3, 4, 5 on the news for a particular hurricane. That is referring to the maximum wind speed in the storm. And then on top of this, I'll mention later when I talk about size, you can define size in a couple different ways. Here, I'll actually focus on, for example, the radius of 34 knots is so the radius where the wind profile reaches that wind speed. And a key point to highlight is just that the outer size, so the size of the overall circulation and the intensity actually vary nearly independently. So you can have large, weak storms, you can have small, strong storms, or any other combination therein. So that's the basics of a tropical cyclone. And so I'm going to lead into, I'll give a little bit more intro about tropical cyclones in the climate system as part of discussing my research. And so I'll talk about my motivation, which is for Earth and the things we want to test. And then I'll talk about implications and connections to potentially other planets for you guys to help discuss or to think about. So again, so I'll start with my motivation. And so all of this work comes from a paper that we published a couple of years ago now in Journal of Atmospheric Science, my colleague Kevin Reed at Stony Brook. So this is the paper here, and you can definitely look it up, or I'm happy to share it with you if you'd like more details and text about our work. So we talked about a hurricane, gave you an intro to that. Hurricanes on Earth, where do they form and what does their climatology look like? So this is a map where you can see the continents in gray. The colors are the mean sea surface temperature. This is from 2000 to 2008. And then their green dots are the genesis points, and then the black lines are the tracks of storms. And so what you can see is that hurricanes form over relatively warm water in the tropics, so low latitudes, though not quite at the equator. So those are the green dots. The black lines, you can see that tropical cyclones, hurricanes tend to move poleward and westward with time. And that's partly owing to what we call beta drift, and partly owing to the background steering flow of the large scale atmospheric circulation. And then you'll notice that as they go to higher latitudes, they die. And so they tend to recurve with the jet stream and die over land, or they die as they move over colder water. And so we'll talk a little bit more about that now, but so that's the basic context of the climatology of tropical cyclones on Earth, the present day Earth. So we can be a little bit more specific and physical and think about the thermodynamics. And so I mentioned before that you can model these hurricanes as a Carnot cycle that gives you an upper bound, a theoretical upper bound on the peak wind speed that an environment could support if a hurricane formed there. And so this is what we call the maximum potential intensity. And so this is in units of meters per second, the color bar on the right. And so you'll notice the colors are generally deeper colors, stronger maximum potential intensities in the tropics, again, where the water was relatively warm. And then when you move away, things decrease rapidly down to zero. So if you want to be super broad about this, is that the tropics, at low latitudes, things are thermodynamically favorable for tropical cyclones. And then as you go to higher latitudes, things become increasingly thermodynamically hostile. And so here I showed potential intensity. So this is just to say the potential intensity decreases moving poleward. And then on top of that, there's a second component, which is that as you run into the jet stream, hurricanes do not like vertical wind shear. They like a barotropic environment. And so the jet stream does all sorts of things to mess with hurricanes as well. So that's the thermodynamic context. And so a hurricane also depends dynamically on the rotation of the Earth for angular momentum. And so this is a topic that's actually received like surprisingly little attention. And this is the focus of our work, is what is the nature of this dependence? And I'll explain what I mean by nature right now. So there's three hypotheses for dynamical controls on hurricanes that we want to look at. And they all, at least the existing hypotheses, depended on the Coriolis parameter F, which may hopefully not be too surprising. So the first is that we have what we call Genesis potential indices, which are empirical measures of the potential for tropical cyclogenesis. And the dynamical component always depends just on the absolute vorticity, which is usually dominated by the Coriolis parameter F, so the local value of the Coriolis parameter. The second question is how close to we said there's no hurricanes on the equator, but how far or how close to the equator can you get? And the existing hypothesis for that, which is a little bit looser, is that maybe you need some threshold value of F at the center of the storm to be able to produce a hurricane, which is also a reasonable idea to think. And then the third one is how large are these storms? And so the existing hypothesis, which is sort of the standard one when you think about vortices, is a 1/f scaling. And so an example of this is shown here. So the x-axis is latitude, moving north or south, and the y-axis is a length scale. And I'm just going to call this an inverse F length scale. And so I'll note here in the numerator is a velocity scale that is not, for hurricanes, is not the deformation radius, or the gravity wave phase speed, which you'd see in a deformation radius, but it said it's a different velocity scale that is the maximum potential intensity, which is often referred to as the natural tropical cyclone length scale on the F plane. So the issue with this is if you look at observations of storm size, which I've done as well, is that it looks nothing like this inverse F length scale. Storm size tends to be relatively constant or maybe increase very slowly with latitude within the tropics and subtropics until you reach the higher latitudes when you run into the jet stream, and then they can grow larger. So obviously this hypothesis is wrong, and we're going to propose a different hypothesis. So those are the three questions, the three hypotheses we're interested in answering. And so I want to zoom out and think about this, is that we're interested in dynamical controls of tropical cyclones, but we live on a world that has both dynamical and thermodynamic variability. So we have at a very coarse grain level, we have planetary thermodynamic forcing for variability, which is that we're a sphere rotating around a star. So you're always going to have higher solar insolation absorbed at low latitudes than at high latitudes. So you have solar insolation gradients, and then you have you also have land and ocean surface variability. And then superimposed on this is what I'll just call planetary dynamical forcing, which is the fact that the planet rotates. And for our thin atmosphere, we think about the vertical component of the Coriolis force, which is F, which goes from 0 at the equator to 2 omega at the pole, so 2 omega sine phi. So that varies with latitude as well. So what ideally, for our purposes, we'd love to think about a world that doesn't have this planetary thermodynamic forcing for variability. And so we'd like to be able to remove the yellow part and isolate the dynamical forcing. So what we're going to do is to start from what is one of the most common Earth-based atmospheric global climate models. And here it's CESM, and this is the atmosphere component, so CAM. This is version 5.3 at high enough resolution to resolve reasonably well tropical cyclones. And so what I'm showing here is this is from a historical Earth simulation, which I'll just call AMIP. And what's plotted in the colors are the near surface wind speed again. And so what we get is this world where you're seeing the rich heterogeneity of weather phenomena that exist on our Earth. So you see the strong surface westerlies in the southern hemisphere over the Southern Ocean. And in the northern hemisphere, you may be able to deduce that this is probably the northern hemisphere summer, because we are seeing, you may see these little circular patches which emerge, for example, in the Atlantic and the West Pacific, and these are tropical cyclones. And so what's really amazing is that we have models that, like people often focus on climate models for the Earth-based stuff and think of all the ways that there are biases relative to the real world. And I sort of think about it in the reverse, is that I'm sort of amazed at the extent to which climate models can reproduce where different types of weather phenomena occur on Earth and when during the year. And they're really pretty darn good at doing that overall. So it's nice then, as we can take our Earth-based model, which we can always compare then directly to observations and ground us in Earth-based observations, and then do experiments with them. And so, as I mentioned, is we'd like to do something where we don't have this thermodynamic variability in forcing for our atmosphere and focus just on the dynamic variability. So we can take our same model and do something different with it. And this is always shocking for the Earth-based atmospheric people that I talk to, but for the planetary folks, it may be less shocking to look at, is we can do this, set the same model up in an Aquaplanet setup where we remove the continents and we make the sea surface temperatures constant everywhere on the planet. And we also make the solar insolation constant everywhere on the planet, which is something that an Earth-like planet going around a star can't have happen, but in the computer model world, we can do this. So let's do the experiment. So this is what's often termed Aquaplanet with uniform thermal forcing. And so what you get is obviously looks, at least at first glance, totally different from the real Earth. And what you end up with, what you're seeing here, is a lot of tropical cyclones. So by removing the thermodynamic variability in the forcing, we've removed, for example, the reasons for existence of a jet stream. We've removed the land and the colder water at high latitudes, all of which act to kill hurricanes on the real Earth. Those things have been removed. And so what you end up with is this world where hurricanes, if you actually look closely, you watch hurricanes still form at relatively low latitudes. They move poleward and westward with time. And you can track one with your eye and watch. And instead of moving to high latitudes and dying like they do on Earth, they sort of just pile up at high latitudes. And they do all sorts of funky things there. And eventually some of them merge together. But they do not, for example, turn into one giant cyclone. So if we want to be kind of a zoomed out view on this, I would describe this as having a cyclone sparse equatorial belt sandwiched between two cyclone filled polar caps. And so what I'm going to try to convince you is actually the cyclone sparse equatorial belt actually is not necessarily all that different from our real tropics on Earth. And so it can be useful to understand tropical cyclones on Earth. Okay, so now we have this Aquaplanet setup, and again, we were not the first to do that, I should say, but this is this uniform thermal forcing world full of tropical cyclones we want to understand and use to understand hurricanes on Earth. So if we go back to our planetary dynamical forcing, of course, we have F, which we often think of as a source of rotation, a source of angular momentum for any sort of system. But on top of that, we also have meridional gradients in F, which is beta. 2 omega over A times the cosine of phi, and so beta, as we know, varies in the opposite sense. It's 0 at the poles and a maximum at the equator. And so when we think about beta, typically we think of this as the source of Rossby waves in our atmosphere. So what I want to bring up is, so I've mentioned that you have this inverse F length scale as kind of an existing length scale within our system, and this inverse F length scale decreases rapidly with latitude. And then if we throw on here what is commonly referred to as the Rhine scale, which is really just an inverse beta length scale with a square root in front of it. This is where beta shows up in the context of a length scale, and it has the opposite sense where it increases monotonically and particularly most rapidly at high latitudes and is relatively constant at lower latitudes. And so this is a length scale. A key difference is that the velocity in the numerator is a resolved flow velocity. It's not a gravity. It's not any sort of a wave phase speed. And so here we're going to just set it as a constant to be 10 meters per second, which is actually a kind of a representative flow speed in the outer part of a hurricane. So this length scale comes up in all sorts of contexts, but it ultimately comes down to it's critical to governing wave vortex transition. So I'm just going to posit this length scale here and not talk about it more at the moment. So we're putting forth this simple idea, which, and again, we're not the first to do this. This actually was proposed also in the oceanography literature and probably elsewhere in places that I haven't seen, is that we have one curve that goes down with latitude, one curve that goes up with latitude, and there's a crossing point, which is just called the critical latitude phi sub c, that may separate two regimes of interest. So we're going to use this theory, use these length scales to understand some of our questions about tropical cyclones on our planet. So let's back out again. So we want to do experiments. So we're interested in varying really these length scales, which depend on F and beta, but ultimately these F depends on the rotation rate, and then beta depends on both the rotation rate and the planetary radius. And that's an important distinction that what we'd like to do is do experiments then varying the rotation rate and the planetary radius relative to Earth in our Aquaplanet simulations, where in particular varying the planetary radius will change beta, but it shouldn't change F. So if something depends on the planetary radius, then that implies that F cannot be the explanatory variable. So what do we do then? We do a few more experiments. So we're going to vary planetary rotation rate and size. So the top middle here is our control, the experiment I already showed you with Earth-like, our Aquaplanet with Earth-like planetary rotation rate and size. And then to the left and bottom middle are doubled, halved, and quartered rotation rate. And then to the right of the black line is, top right is a planet that's twice as large, and then a planet on the bottom right that's half as large. And note that those are not drawn to scale. So you can just see by eye, without spending too much time, that some things seem to be changing. And we're not going to spend too much time looking at this, but just we're going to use these to evaluate hypotheses. But things seem to be changing in interesting ways. And so at the end of the day, we have lots of cyclones on these planets. And so it offers an opportunity to understand how they work. Okay, so now let's get to our three questions. So I mentioned we're interested in genesis rate versus latitude, minimum distance from the equator, and size versus latitude. And again, the prevailing hypothesis for all of these are dependence on F. So let's start with the first question, which is genesis rate versus latitude. So what I'm plotting here is on the x-axis is latitude, again, north or south. The y-axis is genesis rate, a unit per unit area per year. And then the light blue is the real Earth experiment, which we can always compare to the Aquaplanet if we'd like to. And then the brown is our control Aquaplanet. And so what you can see is that on the real Earth, so the dot is the peak genesis, and so the real Earth peak genesis, or genesis peaks at relatively low latitudes, and then in our control Aquaplanet, genesis is able to extend to higher latitudes, but it does reach a peak, and then it decreases poleward from there. And then these dashed lines out here are in the kind of polar, the cyclone-filled regimes, where it's kind of hard to track cyclone genesis to begin with. So, yeah, I think the control gives you about 7 times as many cyclones as in the real world. Okay, so now we want to look at our aquaplanets and look across our experiments. And so what I'm showing here in the browns from light to dark are increasing rotation rate. And then the light green and the red are smaller and larger planetary sizes. And so this is kind of just a mess of curves. Things clearly differ, but our hypothesis was that genesis rate should depend on the Coriolis parameter. And so what we can do is map this into the x-axis into Coriolis parameter space, to F space. And things look a lot less messy. The curves seem to collapse in a particular way. So if you'll notice here, now these curves, the increasing points, or the increase with increasing F seems to be sort of a somewhat quasi-universal across all of these experiments now. And you can actually fit a curve here, and there's a linear fit and then a slightly nonlinear fit. But I'll just focus on the linear fit here in the black, which gives you a slope of about 0.7 with funky units there. And what sets that slope, I have absolutely no idea. That seems like a deeply fundamental question. But clearly across these experiments, there's something that says there's some sort of intrinsic dependence of genesis rate on the Coriolis parameter. So one distinction is you'll notice that these increases in genesis go up, increase up to a point, and that point is up to some value of F. And it turns out that the value of F, the peak where genesis peaks actually scales quite nicely with F at the critical latitude, so the critical Coriolis parameter, if you will. So that's an indication that our two-length scale theory is telling us something kind of fundamental about this system that's useful for explaining its behavior. Okay, so that is the first question. So I think we have clear experimental evidence for the first time that there's really a fundamental dependence on F. And I really should generalize this to absolute vorticity, but especially in our aquaplanets, there's large-scale relative vorticity is quite small, which is another nice convenient aspect of that experiment. So the second question then is the minimum distance from the equator. So let's try to evaluate that. So we're going to take a slightly different approach here. And I've got the answer at the top, but we'll walk through it. So the x-axis now is longitude. So we're sort of looking now as a function of longitude. And then the y-axis is latitude, north or south. And then each curve corresponds to the minimum absolute latitude of storm occurrence in 5-degree longitude bands. And so they're a little bit noisy, but you can see there's some upward and or northward and south, poleward and equatorward shifts. And then there are these stars on the left side, which is we'll define as the median latitude of each curve. So we're interested in the distance to the equator. And you can see it systematically varies, and in particular, systematically varies with planetary radius as well. So that suggests that F is not explaining things here. And so we can propose maybe the second simplest hypothesis, which is to go to our second length scale, is an equatorial either Rhines or deformation scale. So we're taking our inverse beta scale, but we don't really have a way to differentiate what the relevant velocity scale is there. So a deformation scale would have a gravity wave phase speed, but we can't distinguish that here. So I'm agnostic to what the velocity should be. But and so this equatorial scale is on the x-axis here, and then the y-axis is now the absolute distance from this median latitude to the equator, and the experiments are plotted on here, and you get this nice collapse where they scale quite nicely together. So yes, it's not a threshold value of F, which has been thought about before. So what does it really mean? Is the implication is one of storm size, is that at the end of the day, a hurricane is drawing angular momentum inward over some length scale. And so most of the storm circulation then implicitly needs to lie on one side of the equator to have like-signed angular momentum. So that's the physical interpretation of that result. Okay, so we have, I think, a pretty good answer for our second question here. And then our third question is size versus latitude, which is the one where the prevailing hypothesis was clearly wrong. And hopefully you have a sense of where maybe going for an alternative hypothesis. So let's first look at size versus latitude in our simulations. So again, latitude on the x-axis, and then the y-axis, this is the radius, basically almost the edge of the storm, the radius of 2 meters per second. So the overall size of the storm. And you'll note here the solid line, which is the main one you can focus on, is the median. And then there's an interquartile range plotted on there as well. And then the blue, again, is the historical real world simulation. And then the control is our Aquaplanet. And so in both cases, what you'll see is that in low latitudes, low to medium latitudes, you see that size is either relatively constant or approximately increases very slowly with latitude. So they're pretty consistent, at least to kind of first order, between the real world and our control simulation. And I should remind you that, again, that this is also similar to observations, what we see. So that's a good sign. And so obviously a second simplest hypothesis, again, is to go to the Rhine scaling to think about storm size here. And so this is something that seems to be much more consistent with how size seems to vary with latitude. And so I'll note here, the divergence at higher latitudes in the real world is where now tropical cyclones run into the jet stream, and they can sometimes undergo extratropical transition, which is to say that they become, and that it's a process that is an interaction with baroclinic cyclones, and they become larger. So whereas that does not happen in our Aquaplanet simulation, instead at high latitudes, storms eventually reach a peak and then actually become smaller. So they follow more of an inverse F type length scaling at high latitudes. Okay, so we can go one step further in testing this Rhine scaling by varying our rotation rate and varying planetary size. So on the left here is our experiments varying planetary rotation rate from, again, dark brown is the fastest rotation, and then the lighter colors are slower rotation. And so you end up with storms that become larger as you go to slower rotation. So, and the scaling is roughly omega to the -1/2. And then if we go to varying planetary size on the right side here, so again, we've got the smaller planet is in green, the larger planet is in red. And so at low latitudes, you have the scaling roughly 8 to the 1/2, that you get larger storms for a larger planet. And so both of these things are very consistent, again, to first order, to a Rhine's type scaling. And then at high latitudes, things are different, and you have something like a 1/F scaling, but I actually think it's probably even more complicated than that. So, okay, so that is our size versus latitude. And so that we have a Rhine scale as a much better hypothesis from before. So I'll note here, I'm happy to talk about this separately. We spent a lot of time thinking about why exactly does a tropical cyclone care about the Rhine scale. It's a scale that mostly has lived in kind of baroclinic turbulence theory and had not been applied to tropical cyclones, and people did not think that that made any sense. And so we have a new paper that's out in press from my grad student, Kuan-Yu Liu, doing some work with the barotropic model and some simple theory. So I'm happy to talk about that separately, or you can look that up as well. So, okay, so that's the basics. Hopefully I've convinced you at that point that that is at least the low latitudes in on these aquaplanets is relevant to the real world. And my motivation is always to understand how tropical cyclones work on the real Earth, so we can use them, both understand their physics, but also use those physics to, say, make better predictions for their hazards and their impacts. But so now I want to talk a little bit about thinking about other planets, or at least thinking more broadly. And that comes to kind of a really basic question, which is, why is this the qualitative state? Why do we have this cyclone sparse equatorial belt sandwiched between two cyclone filled polar caps? And can we at least have a basic insight from the theory to explain that? And so this goes back to our 2 length scale hypothesis for thinking about our system with the critical latitude. And so I mentioned this critical latitude is really separating 2 regimes. So poleward of the critical latitude is where you have the natural, this inverse F scale, which is kind of like what the tropical cyclone would like to be ideally on an F plane, is much, much smaller than the Rhine scale. And so that's to say that a tropical cyclone can be the size it wants to be, and it's not going to feel beta very strongly. And in contrast, in the low latitude regime, a tropical cyclone wants to be a size that is much larger than the Rhine scale, and so it should feel beta very strong. And exactly, again, the details of how this manifests on a tropical cyclone-like vortex is in that other paper that I mentioned. So it's at the end of the day, this is a ratio of these 2 length scales, which is actually fundamentally dependent only on the product of the planetary rotation rate and planetary size. And it turns out that this omega times A over U is the lone dynamical non-dimensional parameter in the primitive equation that we use for our thin Earth-like atmospheres. So that seems like this is really rooted in something deeply fundamental, at least for Earth-like atmospheres. So what does that theory then mean if we go back to our movie? So at high latitudes in our polar caps, we said that vortices really shouldn't feel beta too much. And another way to phrase that is, if you don't feel beta too much, the flow isn't going to generate Rossby waves. So Rossby waves aren't too important, and vortices can dominate. And meanwhile, in the equatorial belt, Rossby waves are going to be significant because beta is important. And so at least that, like a cursory way to explain it, is that you're going to have a mix of waves and vortices. And so so that's pretty different. And so again, this high latitude regime, so I said this, the equatorial belt is really not fundamentally different from the present day Earth's tropics, but the high latitude regime, we don't see that at all. And remember again that on the present day Earth, this is where the thermodynamics come into play, that these cyclones were thermodynamically suppressed on the real Earth at high latitudes. And so we can actually go one step further. So these high latitude regime, another way to think about it is, and I think Yohai Caspi mentioned this even when talking about Jupiter as well, is when you get to these high latitudes, this is where beta is small. And so really the dynamics are similar to an F plane. And there's a ton of work, including what I had shown earlier, showing that on the F plane, not only do cyclones form spontaneously, so this is an F plane over a constant sea surface temperature with an atmosphere that's just cooling radiatively. Storms form spontaneously, and they also fill the domain. And so that's actually what you're seeing here is a box. It's just an atmospheric, a doubly periodic box with a bunch of cyclones that fill the domain. And that's essentially what you see at high latitudes in the polar cap regime. So we're really kind of extending the F plane into the dynamics of the F plane into this domain of the sphere. Yeah, and just so, again, to put it, another way to put it is, without variations in F, there's no Rossby waves to disrupt the vortices. So you have vortices that, if they form spontaneously or however they're formed, they can last a very, very long time. And I know Georgie also talked a fair bit about why vortices, other more complicated things for why vortices may last a long time. An additional point that we can actually compare with our theory is, so if you look across the experiments varying planetary size, where this works really well, you'll notice that just qualitatively by eye, as you go from a smaller planet to the left to a larger planet on the right, it's as if you have a larger fraction of the surface covered in cyclones. So the polar cap seems to expand equatorward. And so this is something that can be understood in the context of this 2-length scale theory, is that as you increase your planetary size, what you're doing is effectively reducing beta everywhere. And so that increases your Rhine scale, your beta scale. And so that shifts this dashed curve upwards. And so that's going to move the critical radius, this kind of transition radius between the two regimes equatorward. So that's what we're seeing in these experiments. So what I will say, though, is that in the experiments varying planetary rotation rate, this transition latitude doesn't seem to change much. And that is not what would be predicted from theory. So something else must be going on in that context. That is one thing the theory does not explain. So yeah, and so what I'll say is, in thinking about other planets, is that this world that we created to try to understand Earth, I think is really probably more analogous to an internally heated planet. Or at a minimum, sort of a horizontally homogeneous convecting atmosphere, a planet with a deep convecting atmosphere. So, and so it has relevance to the real world, but it perhaps has much more relevance to some other planets, especially this high latitude regime, where you have lots of cyclones. So yeah, and I actually moved fairly quickly through that. So I guess I cut out more than I should have, so that'll be fine in time for discussion. So I'll just end here with conclusions of tropical cyclones on Earth-like planets. So Earth-like atmospheres, which I guess I define generally, at least we're here thinking about thin convecting atmospheres without large-scale baroclinic forcing, may have cyclone-filled polar caps, which looks very different from the Earth, but the equatorial belt of these planets can be used to understand tropical cyclones on the real Earth, and that's really nice. Even maybe from the planetary perspective, as it means that that gives you grounding to be able to compare understanding directly with observations from the real Earth, which is pretty cool to connect across Earth-based observations out to kind of other planetary atmospheres. And so a couple other points I want to make is that, so the surface flux driven physics that I talked about for how hurricanes work, it promotes what I just would call a hurricane pathway to generating vortices, and it's quite efficient. The time scale on Earth for generating a hurricane is on the order of a day. But that doesn't mean that's the only way to make vortices. And I know, again, Georgie's talked at length about this topic, and there's lots of different ways to make vortices. Certainly at high latitudes, the fact that you have background rotation means there's sort of a propensity for any sort of flow to generate rotation. And so I don't think this is a mutually exclusive thing, but it's another pathway to think about that. If, for example, you have a surface, or even, I'm not sure to what extent this could generalize to an atmosphere that doesn't explicitly have a surface, but it's a specific physical pathway that it can be quite efficient at generating vortices. And actually can also, that is quite robust in maintaining them if the thermodynamics are friendly enough. So, and then a point again, just relevance to other planets. I mean, listening to Yohai's talk about Jupiter, you know, he seemed to make an argument that I don't know a lot about deep atmospheres, but he seemed to make the argument that they're at least reasonably barotropic in the kind of weather layer component. And so I'm not quite sure how it extends to Jupiter, but maybe there's some relevance there. I'm not sure. So, so yeah, with that, I'll stop there. I guess I have plenty of time for discussion or questions. I'd be happy to talk about anything, or even if you have other things, I have backup slides if there's things you're wondering about I can bring up. All right,
great.
So
That's just super. Thanks so much, Dan. Super interesting. And I can't wait to see the vacation poster for this planet.
Yes.
Oh, you
I
like
used to talk about
hurricanes.
that.
You're gonna love this planet. Okay. Yeah, let's go with the questions. So James.
I didn't quite catch at the beginning. What is your ocean like? Is it constant temperature, or does it have a mixed layer that would erode and get colder as the hurricane
So no dynamic ocean. It's just a constant sea surface temperature. So running an atmosphere only model that has a surface, and the surface is constant everywhere. So without question, we're neglecting any sort of ocean feedbacks that might be at play here.
Yeah, I'm just
or surface feedbacks in general.
As it gets the higher latitudes, they seem to move more slowly, and I wonder if they'd run out of they'd eat up all the local heat
Yeah, so I think at the end of the day, there has to be something, the implicit, that's where I kind of made an analogy to an internally heated planet. There has to be ultimately some sort of a heat source to maintain the surface temperatures at that temperature. So whatever that would, whether it's external or internal, I don't know. But yeah, eventually they're basically sucking heat in both temperature and latent heat forms out of the ocean and using that to generate a circulation. And so somehow, I mean, I guess technically the energy sticks around, but you're generating entropy. And so there has to be some sort of a restoring mechanism in place. It can't truly last forever.
Yeah, so in some sense, it may work better for a planet that's heated from below.
Exactly, yeah. I think that's the best analog. So I'm not sure. Yeah, I think that's the only, like, to me, otherwise you have to come up with some sort of funky configuration. To me, any sphere that goes around a star, you're just always if heat input is significant from the star, I don't see how you don't end up with like a pretty strong meridional gradient in heat input, which is going to disrupt this significantly. So.
Okay, thank you.
Yeah, absolutely.
Do you want to handle calling on the people as you see fit, Dan?
Sure, I can do that.
Sure.
I'm not sure who had hands up first. I'll go with Dennis or Denis. I don't know it.
Dennis, yeah, thanks.
Dennis.
Yeah, thanks. That's a great piece of work and very interesting study. So, if I understood you correctly, all these experiments were done with a moist atmosphere, right? Have you done any purely dry simulations? And if so, are the scaling relations similar there?
We have not done a dry planet. We have talked about it for a long time, but we have not done it. What I can say is, let me see here. So on the F plane, we have done simulations on a dry, let's see if I can bring this up. On a totally dry atmosphere on the F plane, you also will spontaneously generate vortices. And this is the video, what they look like. And so the colors are more muted because they tend to be weaker. They tend to be much more variable. But fundamentally, it's what ends up happening is in a dry atmosphere, you are fueled by, if you still have, the atmosphere is still cooling radiatively, it's sensible heat fluxes rather than latent heat fluxes that balance that. And so it's still a heat input that can be used to generate a circulation, but things are much noisier. So we haven't done the dry sphere planet. I don't know, time just goes by and we've talked about it, but my guess based on this is that things will be much, much messier because the vortices, well, a key thing that we find, and like, so this is from a planet where we compared dry and moist and even semi-dry atmospheres, is the moist vortices are very stable. Like their structure is very stable. There's something about the condensation of latent heat and the energy associated with that even though that itself is not like, the hurricane just needs energy input of some kind to exist, but the stability of the structure and its ability even to potentially to kind of, what's the word, to separate itself from the variability in the environment around it is much stronger with moisture than without it. So,
what do you mean by
semi-dry in this context?
Semi-dry was an atmosphere where what we did was turned down the evaporative potential of the surface from a moist surface to a dry, and in the middle, if you have so semi-dry means like you could think of it as sort of like half water, half land. And so surface fluxes are kind of a mixture of sensible and latent heat. And actually, if you have that, you don't get cyclones. There's something about the system that does not produce any cyclones at all, which we don't really know why that is either. So yeah, it's either like fully moist or fully dry, but a mixture in a homogeneous way. Like obviously the real Earth has a mixture of land and ocean, but it's like homogeneous ocean and homogeneous land. The semi-dry, it's like a sort of hybrid ocean land surface. So.
And it was only half and half in terms of evaporative capability, not in terms of like friction or anything like that.
Yep. No, just
okay.
just the evaporation. Yep. We didn't touch the
Right.
drag part. So, but certainly, if with land with higher drag, you'd expect the vertices to be even weaker. So.
Okay. Thank you.
Yeah. Great question. Raul.
Hey, can you hear me?
Yes.
Oh, hi. Yeah, well, first, I wanted to thank Jonathan for organizing this series because it's amazing and it's very fun. And also, thanks for presenting this. This is pretty cool. I have a question. I was wondering, have you looked at how the size of your of these spots that show up in your simulations relate to the rate of available potential energy and kinetic energy?
So no, we have not done that. There's another group, Diane at UC Davis, who's working on that, who's looked at that. But no, we haven't. I have a postdoc thinking about this. We're trying to understand the temporal dynamics of a size, which are really complicated. So storms actually can be really, when I talked about size here, I was talking about the median size, but there's actually a wide variability in size relative to the median. And so that's something we're trying to play around with some simple models that take that approach, but otherwise we haven't.
Okay, once you do, please let me know, because I've been involved in a couple of papers dealing with polar models of Jupiter stuff. Cool. And that's one of the analyses that we did. And we did find that the size of the spots is proportional to this ratio. And so if you are to explore this and find something similar, I would be very interested in knowing about it. Okay.
Can you send me papers, or I'd love to.
It's still under review.
Okay, gotcha.
As soon
cool.
As soon as we get it through, I'll let you know.
Okay, sounds good.
But yeah, from a comparative point of view, I will be very interested in seeing what you find when you do the energy analysis.
Okay, yeah. Yeah, the truth is we haven't actually spent that much time on the polar cyclones, because that's not the part that is relevant to Earth. So that's always been like, I always get lots of questions about them, and we didn't, other than kind of describing the qualitative state, we didn't spend too much time thinking about it. So that's good to know.
Yeah, I understand, but I think it's great. I love to see things, how other people doing different things. Like you say, oh, we're doing Earth, so maybe this doesn't apply, but in the end, everything is related. So I think it's just fascinating.
Yeah, no, that's why I'd love to see what you guys did too, because that sounds, I agree, the opposite direction. I agree 100%.
Yeah, and the experiments were very similar. We were also exploring different rotation rates and planetary sizes. So anyhow,
cool.
Yeah.
Yeah, I will say, I mean, I mentioned that the size, size decreases in, here, let me bring this up again, in the polar region, but we gave there was like a qualitative sense that obviously it decreases moving poleward above equator or poleward of some peak. And that is generally consistent with the 1/f scaling, but it's not at all, it doesn't actually, across the experiments, it doesn't actually scale with 1/f. And so that is where we sort of just left it and said, well, I don't know, there's something else going on. So maybe what your approach may be much more insightful. So.
And you said that the spots in your simulations, they actually don't interact with each other, or don't interact with each other. You mentioned at the beginning that they don't merge. Is that correct?
They do occasionally. So if I bring it up, let me scroll over. So that, in the end, a thing we actually only thought about kind of afterwards is, let's see here, there we go. So if you watch the movies, so they do occasionally merge. They don't ever seem to die. So here's one, they dance around.
Oh yeah,
Yeah, so every once in a while, if you see, it's, there's a lot of literature on mergers of vortices. Ooh, that one just happened right there. So if you have a strong vortex near a weak vortex, they will merge. And at the end of the day, we don't really see evidence that a vortex ever dies on its own. This is where the environment is really favorable. And so I think, but there's a supply of vortices constantly from lower latitudes. So something to reach equilibrium, you need to have a sink. And I think the sink is that there's the mergers of the vortices. But again, we didn't try to do anything fancy to track that or look at that in this.
All right, well, cool. I'll keep an eye out for your energy analysis.
I don't know if I'll do that. I will definitely, I'll reach out to you because I'd love to know whenever you have a paper available. I'd love to see what you guys are looking at, see if I can think about it more. So,
all right,
thanks, Raul.
thank you. Yeah, no problem.
And Peter, I saw you were raising your hand.
Oh yeah, it's very interesting. A great talk. I really enjoyed it. Well, of course, I kind of miss seeing zonal jet streams, which is understandable in the sense with not having the zonal varying heating and overturning circulations. And also the difference in Rossby number. I mean, cyclones, tropical cyclones with Rossby numbers of somewhere near 1 and Earth terrestrial things with lower Rossby number seem to give you a lot of jet streams and things. And do you have any more to say about that? And also, did I see poleward migration in the high latitude of the cyclones, which has been featured in some other recent papers?
Yes. So yeah, I mean, all the cyclones migrate poleward under beta drift. That's ultimately, there's no large scale circulation to move them poleward like there is in the real world. And so yeah, like, I mean, with Yohai, his work showing, trying to explain why there's this certain number of cyclones in the polar caps of Jupiter and Saturn is a barotropic argument that's fairly, like, to me, aligns very closely with this. So so they do drift poleward. That's why they do in our simulations. In terms of the jets, yeah, so we don't get, you actually do get a weak easterly jet, but I think that actually has nothing to do, let me bring this up here. This is a cross section latitude on the x-axis and pressure on the y-axis. And so the negatives are weak eastward or easterly jet. That is, so like these numbers go up to 10 meters per second. But this, I think, is actually mostly because the cyclones themselves, the high latitude polar cap cyclones, have a feedback on the atmosphere that warms it relative to the lower latitudes where there are fewer cyclones.
Mm-hmm.
And there's some work that's argued for this. And so, but yeah, otherwise, we don't get spontaneous jets. I don't know why. I don't know if we are supposed to or not. To me, I think of this as sort of I don't know. We don't have any explanations for why. That's just what we find. So, and I'm not a jet expert, so this is where I don't quite know.
I guess there are lots of differences in configuration in the Earth and the planets and the aquaplanets. But I struggle, being a not terribly educated atmospheric scientist, better educated as an oceanographer. I struggle to think about the vertical velocity in tropical cyclones versus the vertical velocity you see in more quasi-geostrophic cyclones and anticyclones on the Earth. Could you say anything about that? I mean, the very strong hurricanes are intensely rising in the center, and the low Rossby number things, the vertical velocity is, it looks to me like it's more the cyclones plowing like snow plows and making comma-shaped upwelling and rain bands, atmospheric rivers they're called, but they're not really rivers at all. But these wonderful comma-shaped narrow regions of upwelling, and also frictional Ekman driven upwelling in quasi-geostrophic cyclones. Could you illuminate about on that idea of vertical motion in these things?
I mean, the simplest answer would be, usually the vertical velocities are something like 1/10 of the maximum wind speeds. So you can get like 10 meter per second vertical velocities in tropical cyclones.
Mm-hmm.
I'm not sure. The second part of your question, I'm not sure, because I don't know the reverse. I'm not sure what vertical velocities are in quasi-geos. And you mean like in just baroclinic cyclones, or in extratropical cyclones? Oh yeah. I don't know. That's a good point. I guess I actually don't have in my mind what a typical vertical velocity is in an extratropical cyclone, but certainly, I mean, I know within strong thunderstorms in the warm sectors of extratropical cyclones, you can get really fast vertical, like you can get 40, 50 meter per second vertical velocities, but I guess I kind of think of them as probably similar orders of magnitude.
Yeah, this kind of this spiraling upward on the edges of the extratropical cyclones that my colleagues tell me about, but I've never understood. And it's important in the sense that I love to teach GFD throughout many years, and I love to talk about Carnot cycles and the cycling of a heat engine on a pressure specific volume plane, and the enclosed area in the path is the conversion of heat energy into mechanical energy. Beautiful story. And I keep saying, well, look at a convecting fluid. Its parcels are cycling and they're heating at high pressure and cooling at low pressure, and that's how it works. But it's that analogy with the parcels and heat engines is not at all clear to me. I mean, there's sets upper bounds to the amount of energy you can get from a convection. But is there a good thermodynamical connection that one can drag out of this to illuminate that?
For tropical cyclones or for in general?
Well, either one. I mean, parcel arguments in real fluids the parcels are not isolated the way they are in an idealized 101 class of heat engine.
Yeah, I mean, I think what I would say, I agree. Applied to the whole atmosphere, it's always a little bit like it always sets an upper bound. And for the atmosphere, it's obviously much less efficient than an upper bound. For a tropical cyclone is about as close as you can get to the most efficient cycle, like a Carnot cycle. There's a whole lot, I can just tell you, there's a whole bunch of debate about exactly how to think about the cycle. But Carnot cycle theory, which is it's just a couple of equations. It simplifies to a couple of equations, gives us a prediction for the maximum wind speed of hurricanes that works really well compared to observations. And maybe there's like a scaling constant in there, but it's like remarkably good. And so part of that is that in a tropical cyclone, air rises in an environment that is nearly saturated. So there's very little re-evaporation of, or there's very, very little like condensate. Water evaporates out and falls to the ground. There's very little re-evaporation, and that is a significant, what's the way to phrase it? That's a significant reduction in the efficiency of the engine.
I see.
The heat. It's really a steam engine at the end of the day. It's like the proper way. There's a more general form that accounts for moist processes that Olivier Paul-Wies has worked through in detail. And so really it's best to think about it as a steam engine, and there's a huge energy penalty from entropy production from irreversible processes with changes in the phase of water. And so the tropical cyclone, it has created, it's sort of a system where you have condensation, which is reversible, but then you don't have rain falls back through, and you don't have much rain falling into dry air that then re-evaporates. And so it's still not perfect, but it's actually pretty darn close to being as efficient as you can get.
Well, thanks very much. That's a really good introduction, and I'll go back to my textbooks.
Great, wonderful. This is a great time. I'm sure there's still more questions. I know I have a bunch. So it's a good time to end the official talk and stop the recording.